to University of. He went to University of Oxford for as a Marie Curie fellow for his postdoc. Then from there he went to he went to Korea uh, as a junior group leader at APCTP Pohang, and now he is currently based in Daejeon at Kasi, Korea Astronomy and Space Science as a professor. So yeah, let's welcome Professor Arman, and the stage is please start.
Thank you very much, Pawan, for the nice introduction. Yeah, in fact, Pawan was a postdoc with us in Kasi, not for a long time, and I still remember that the food issue should be taken very seriously. I think Pawan had some problem with the food here, so after Pawan, any postdoc comes. No, seriously, I have to warn them from the very beginning. Be very careful about the food. That's particularly for the vegetarians. But anyway, thank you very much for the invitation. I'm very happy that this CMB Bharat activity is still going on. I hope that we will see Indian CMB space mission in the space. And I think with the large group of young, enthusiastic, and really good researchers, scientists in this field, I think this is not really out of imagination. I know that this is a Durga Puja and it's a holiday time, so yeah, I expect not so many people to attend. But anyway, it's recorded. Maybe people can listen later. But anyway, I'm happy to be here. So yeah, so I'm going to talk about reconstructing dark energy, and the subtitle is "Could we be fooled by the phantom crossing?" So this is a very interesting subject. It used to be one of my main subjects up to about 10 or 15 years ago. So I used to give talks on reconstructing dark energy till 2012, 2013 or 14. But after that, we shifted to the other things which were interesting. It's still reconstructing dark energy is certainly important. But anyway, it was something, but since the data was very close to lumpdecidium, we had less, it was less on the highlight. It was always important, it was less on the highlight. So let's have some very brief review of the situation. We are in the era of precision cosmology. I expect that everyone here is a cosmologist or student in cosmology, so I don't need to go through much of the details or introduction. Maybe I try to finish even my talk faster than usual, and then we have some time for discussion. But anyway, we are in the era of precision cosmology. We have all different cosmological observations, from cosmological background to the large-scale structure information, knowing the location and the redshift of the galaxies. We have type 1 supernova with standard, which are standardized candles. We have option of lensing from the weak lensing or strong lensing. So we have lots of things, and with combination of all these theoretical works and measurements and statistical techniques and computations, we have been able to constrain basically parameters of different models, or having some idea about the models. So cosmology is a science of everything, right? So we are trying to understand the universe in its largest scales. So there are very big key questions involved. It's related to the initial condition, which how universe started, the seeds of fluctuations and perturbation. We need to know about its metric. We need to know about its curvature. We need to know about its dark sector, dark matter, or dark energy. We need to know about reionization and loss of astrophysics. We need to know about neutrinos, radiation, baryons. So there's lots of unknown things. And we have this phenomenologically simple lumpdecidium model, the standard model of cosmology, lumpdecidium model that is simple in a parametric way, in the sense that we have only with 6-7 parameters we can describe the whole dynamic and evolution and initial condition of the universe. So we spend only 2 parameters for initial condition. It's like a power law, and then we try to describe we assume the metric is a Fuller W, which makes sense because of the overall we can say the universe is homogeneous and isotropic. We assume the flatness, we assume dark energy is lambda, we assume dark matter is cold. So you see that there's lots of assumptions in this standard cosmology. But these are reasonable assumptions in the sense that the standard model has been working pretty well. So if you look at, for example, the supernova data about 25, 30 years ago, we had only a handful of supernova, which basically the two groups in Harvard and Berkeley could discover accelerating universe or confirm accelerating universe. There were hints about that before by about 60 type 1a supernova. But now we have 2,000 plus. We have 3 main compilations, and the standard model is pretty well matched with the data. The cosmological background, about 30 years ago, we barely had even the first acoustic peak. And in fact, when I started research in cosmology, started basically my master projects with Tarun Souradeep back in 2001, we didn't have even WMAP, right? So when I started exploring cosmology, this is the data that was available at that time, and everyone was waiting for this groundbreaking WMAP data, which is going to go to the second, third peak of the acoustic peak. So now, Planck is already getting close to 10 years old now, but now we have a very nice, measurements of the angular power spectrum. And again, when you go to the residual space, everything seems to be pretty consistent to the standard model. So standard model is a combination of assumptions, but it's a combination of reasonable assumptions. It means that these assumptions are good. These assumptions make sense. Lambda is a very simple term. It's been Daejeon equations, Friedland equations from the very time. It was removed, it's come back. Power law is supported by the inflationary scenarios with the single field mechanism. We can basically generate a slow roll mechanism. We can generate Pavlov primordial spectrum. Universe look isotropic homogeneity. So FLRW metric seems a very reasonable metric, combined with the GR. Flatness again is supported by not only by the inflation but also by the location of the first peak of the CMB acoustic peak. So yeah, a standard model is a combination of assumptions, but they are all very reasonable. So the situation was nice till about 12 years ago when the Planck data first release come out, and then we realized that when you feed the data to standard lambda CDM model, since the data is powerful, the error bars become tiny, and we end up around 67 plus minus less than 1, and which was in a kind of a tension with the local measurements. People were skeptical, wait a couple of years, but Planck 15 confirmed the Planck 13 results, and Planck 18, practically the final release, confirmed the final results, and then we end up with 4 plus tension. So the tension has not been only in the H0 and CMB. Practically, if you fit other cosmology data, like for example, in the left panel, you can see these are results from the BAO from the DESI. If you just combine Big Bang nuclear synthesis with some scales from the CMB and BAO, still you get the H0 value, assuming lambda CDM, not consistent with the late time observations. There have been also some kind of attention in the S8 or growth of a structure, even though that's not as strong as the Hubble tension. But yeah, there might be something, even though it's not very strong. So in the last 10 years, there have been lots of attempts to resolve the tensions. One could basically say it's about the statistical fluctuations, but not anymore. When we go beyond the 4 sigma, it's hard to explain things with the statistical fluctuations. Systematics in one or some of the data. In my opinion, this is the most probable scenario. I have my reasons, but considering the complications of the tensions, that they cannot be resolved by minimal modifications, I strongly think that the reason behind it could be some systematics in one or some of the data. Another way is that extended models or new physics, which there have been hundreds of papers to explain things. One fact is that majority of the extended models have not really solved the Hubble tension. They just fit the data better than the Lambda-CDM model. And since they have more degrees of freedom, your confidence contours were inflated. And so they have kind of reduced the tensions. But it is practically, you know, I certainly don't call it resolving the tensions. I'm not saying it is bad to do that, but yeah. Okay. So tensions have been there, and as I said, you know, we can come up with some new physics or some extended models to try to reduce the tensions. However, I should say, emphasize here that there have not been really a solution to Hubble tension so far, and I'm not sure even it exists. But one thing which I want to emphasize here, and maybe one of my my key point of my talk here, is that it's about dark energy. That dark energy is a very important part of the standard model of cosmology. It's directly related to expansion history, growth of structure, and many of them has been proposed to alleviate the tensions. None have been successful. But this is my the most important key point of this talk is that understanding dark energy is important, with or without tensions. Okay, so tensions may remain, tensions may resolve, which I give higher probability the second. But understanding dark energy is very fundamental. It's very fundamental, and it's very important that try to separate these two problems together, because if I believe in the tensions and I believe in all of my data, and if one of the data is wrong, there is systematic one of the data, it's like that I'm trying to solve a problem which I should not solve, right? Because the data is wrong, and I'm trying to force a model to fit the data which is wrong. Right? So it's important that, you know, to understand that the tensions in cosmology and dark energy, understanding dark energy, are connected. But it's also important to understand that dark energy, understanding dark energy, is independently important. It's even very fundamental question. Okay. Why dark energy is important? It's drive the acceleration expansion. It's a very weird force, right? I mean, we don't have it in the standard model. So it doesn't exist in the standard model of particle physics. A string theorist hates it, right? I mean, you know, because the dositor space with the positive quadratic constant doesn't fit at all in the formulation of the string theory. So they don't like dark energy. They don't like acceleration. And and it is there. We can see it observation. Philosophically, it is very important because it shapes the face of the universe. I mean, I know it's nothing to do with us, that what would happen in the universe 200 billion years later, but still, you know, we can enjoy your imagination, and depends on the model of dark energy, we may end up with different fates, very different fates. In fact, it's possible that we end up, if the standard model is correct, we may end up with just some of the neighboring galaxies, so far away from other parts of the universe that we may not be able to observe any of the galaxies. But key point which connects cosmology and theoretical physics is that it challenges our understanding of physics. It doesn't. Dark energy is not a part of any fundamental theory, and so it's very important. It's very important at the same time from a practical point of view. We know that it exists. We know that it has some special behavior. So we want to design our future experiments to study dark energy. So yeah, I mean, it's a quest of century. It is something that we certainly like to understand what it is and how to explain it. There are probes of dark energy. I mean, we have standard candles, we have standard rulers, like a BAO, standard candles, like a supernova, and then we can use growth of a structure. Again, I think most of you guys have passed the cosmology course, so you know whatever is going on here. But to move forward to understand dark energy, you know, I will go with the two main approaches: reconstruction and falsification. Reconstruction is about understanding the behavior, and falsification is like a hypothesis testing, that, you know, they're trying to test the consistency and validation of models. So validation is another key point of my talk, which I will come to later. So why falsification validation? Something very important, maybe this is the second key point of my talk today, is that some model, when you have a data, some model can fit the data better than the others. But what if all these models are wrong? Okay, so in the context of the Hubble tension, as I said, there are hundreds of papers which try to explain the Hubble tension. Sarcastically, people have used my own model, like the model which we developed with the Starobinsky and Varun, to solve the Hubble tension. And paper come to me that, oh, we solved the Hubble tension using this model, and it was crap, right? It was not really, they're not really solving. Yeah, the model fit the data better than lambda CDM, but it doesn't mean that that model is correct. This is the importance of the model validation. So the point is that when we use even the sophisticated statistical approach, to my opinion, is not very sophisticated. Bayesian evidence approach. I mean, cosmologists look at this like a very great thing, but it's like a few hundred years old concept. We just compare the models, we rank the models. So for example, in this paper a couple of years ago, we showed that, for example, if you have two models, you have, for example, phenomenologically emergent dark energy and the lambda CDM model, and you compare them, while the mother model is another thing, right? The mother model is another model, is none of these two. And then when you compare them using the Bayesian evidence, you always find one of the models better than the other ones, right? For example, here, with Bayesian evidence, with a very high confidence, I can rule out the favor of the lambda CDM. So lambda is never ruled out because Bayesian evidence just tells you who is better than the other. And that's where it's important for the validation. So validation is something that allows you to validate the consistency of a model to the data without comparing it to the other models. I'm not caring about the ranking. I want to say that if my model is consistent with data or not. And here we show that it's possible, for example, this I-20 validation approach, which we show that, in fact, if we can, in the same kind of simulations, while Bayesian approach was just preferring one model to the other, we can basically, like, at 95%, rule out 92% of all in all realizations. I can rule out both models, or in 80% of the cases, I can rule out both models at 99%. So practically, I'm not able to tell what is the right model, but I can say that, okay, none of these models. Okay. And I think this is very, very important. One application of model validation is a paper with Ryan Kill, my postdoc a couple of years ago, that we showed that practically, when we come up with a very, very extensive physical space, and we try to do the concept of the validation, and we practically show that none of the existing models really solve the Hubble tension. None of them pass the validation. Some of them are better than the other one, but none of them solve the tension. So we got it ruled out in physics at low redshift. Yeah, it was a PRL publication, and I think it was a very good work to show that, look, yeah, you can have a model better than Laplacian, but that doesn't mean that you are fitting the data better, as you see in this red ellipse. That, yeah, I mean, the majority of these models still, doesn't give you the Hubble parameter close to 67, close to 73, 74. As you see here, the extended Chebyshev polynomial extension crossing model, it gets closer, but it doesn't really overlap within the range that I expect from Schu's collaboration. So yeah, it's important to validate things. So this may be another important message of my talk, and at the same time, these validations may guide us towards another corner of physics. So, for example, honestly, rather than focusing on the dark energy model early or late, which I certainly confidently say there is no solution early universe or late universe that can solve the problem. But it might basically say, okay, what about, going and play with the homomorphic model spectrum, which I think is a very interesting approach. These are the projects which we started with Tarun back in 25 years ago. And still, things are moving on forward. And if someone is interested, there was some kind of early universe inflation solution to the problem. Again, this is just sorting out some of the anomalies. But yeah, the Fabio Pinelli and Diraj Hazra. Okay. This slide basically shows overall the statistical approach which I propose. Is that, okay, now we have the validation, which is important, and I can use some special techniques to do that. But if I want to understand something, the behavior, it's also important to do the reconstruction. So there are two main ways to do the reconstruction parametric approaches. It's like you have a model fitting, basically. You have a parametric form, you have a, you basically just fit your model to the data. And then you have, but the result is that, usually biased by the assumed model, by the assumed parametric. And then you can have non-parametric methods, which are difficult to apply. It's not only difficult to apply, it's difficult to construct and implement. Happens that many times people, something is going wrong. But if you do it properly, it is less biased and more reliable. And also you can go beyond the theoretical models and assumptions. At the same time, you can use it for model validation. With some tricks, you can use it for model validation. My general approach is that it's very good to do the reconstruction in the non-parametric way. Get a hint that what kind of a behavior your data suggests. Then do the phenomenology, basically trying to come up with the functional forms that generate that, and then try to come up with a theory. Okay. So maybe the paper I mentioned, this one with Akel and Fabio and Diraj, which was a PRL paper on inflation. You know, many people work on inflation. There's, oh, how can you write PRL there? Okay, the point was that we did the reconstruction using Richardson Lucy. We knew what kind of a behavior we need. And then we tried to come up with phenomenological behavior. And then we tried to construct a theory. So practically we knew what we want. Rather than having a model to fit to the data, we know what kind of model we want because we have done the reconstruction. We know what kind of a behavior I want to expect from the data. So parametric form of dark energy, again, you guys know about that. We have the DL, we have connected to the H is connected to dark energy density to the equation of state of dark energy, and the W of Z. Okay, this is for the flat universe. The most common way is that to use parametric form for the W of Z. Yeah, this is the most common way that people use. There have been issues with the CPL or Chevalier-Polarski-Linderanzat. In fact, this is my first dark energy paper with the Varun, Sahni, Alexei Starobinsky, and Ojemi. That basically we showed that for some particular form of dark energy, using the CPL is not working. For example, here there's a singularity in the equation of dark energy. The H of Z is well behaved. When you use CPL, you get this kind of a quintessence behavior which crosses to the phantom, and it's completely missing this dashed line. It's completely irrelevant. So there we suggested the method of iterative smoothing, which is a pretty sophisticated approach after several developments and modifications. There's another example by the Salman Habib groups that basically this is a paper they introduced Gaussian processes. That if you have such a form, this form is not crossing the phantom divide line. By phantom divide line, I mean W equals -1. But if you use a CPL, you get this behavior. You are first of all missing the true model at more than 2 sigma at some important range. Let's not forget that relative lower than 0.5 is a very important range with the dark energy dominating. It's like the last 1 billion years of the universe. And it's also crossed the phantom divide line. So it's practically the artifact of the parametric form because it doesn't have the flexibility to make such a form. So yeah, interestingly, this was the reason I got to know Eric Linder and then later become a very close collaborator. So non-parametric approaches usually involve binning and smoothing in the sense that, I'm going backward. Rather than trying to model the DL, I said, okay, what if I have the DL and I smooth it and I try to get the derivative of that and I get H of Z, right? I can do that. But I need to do a very good job to smooth DL very nicely in a nice way, not introducing any bias. And if I have H of Z, right, and if I can get the second derivative of H prime, then I can even reconstruct W of Z. So I need to have a good reconstruction of H and good reconstruction of H prime. And I need also to know momentum. So, people who worked with the data, they understand that, when you take the derivatives, this error propagation is crazy. And it's not very easy to do all these things. But yeah, as I said, it's a challenging problem. There have been 2 main approaches that have been involved in the last 10, 15 years. One has been Gaussian processes, the modeling the data around the mean function. In fact, we have been written one of the first papers of the most conventional, probably is the first paper on GP, on the most conventional way to use GP, with Alexim and Eric Linder back in 2012. It's a good way, but I really strongly suggest people to write your own code. The packages exist, have problems. I'm not going to talk about that, but yeah, that's certainly a case. Even we have a paper a couple of years ago about how to use GP. So if someone is interested, I really recommend to read that paper. Because the effect of mean function is pretty important. Another one is the crossing statistical Daejeon interpretation, which is a comparing model its own possible variations using the hyperfunction with orthogonal. So little bit of the crossing statistics. Crossing statistics is something which I proposed many years ago, 2010, and it's one of my my dear children, which I really like. So the pillar of the statistic is very fundamental but very simple. It means that if a proposed model is different than the actual model, right, then they cross each other at 1 point or 2 point or 3 point or n point or no point. Yeah, we have one model, for example, here they're crossing each other at 1 point. Here they're crossing each other at 2 points. They can be completely off, right, not cross each other, or they can basically cross each other. So practically, these two models, they cross each other at 0 point or n point. It looks like absolutely obvious, right? It's basically very obvious. And that's the reason I like mathematics, that we can start from something so obvious and construct. So I get interesting things out. One key aspect of crossing statistics is about the connecting the likelihood to something beyond the chi-square. Okay. So this is a very, again, a key point of crossing statistics. For example, imagine that I have two models and I'm fitting the data and I'm going to the residual space. Residual space means that it's left and right. This is a subtraction of the model from data. Right? In one end, I end up to the left one, and right side, I end up to the other one. Both these cases have the equal chi-square. Okay, they have the chi-square, same. But do you think they are equally probable? Right. So that's the way that we connect the chi-square to probability. And the problem with the chi-square is that chi-square look at the whole thing together. It doesn't care about the sequentiality of the events. Okay. So one example which I give to people about crossing statistics is that, like, I give you a coin and I ask you to throw it away 100 times, and I want to judge if the coin is a good coin or is not a good coin. So that's the equal probability of the tail and head, or it doesn't. And the chi-square just care about how many times it is tail, how many times it is head. Okay. So if I tell you it is 49 times head and 51 times tail, you will say, yeah, that's a good coin. And it doesn't care about how these tail and heads have been come after each other, the sequence. So for example, if in one of the coins I threw it and the first 49 times it is head and then 51 times it becomes tail, something is weird, right? It's like I'm throwing a coin for 50 times, always head, and then tail. So chi-square don't care, just care about the total. And that is the essence that the crossing trying to get at. Right? By using a crossing, we can find out that these two cases, left and right, are not equally probable. This guy is much more probable than this guy. This guy is actually very important. So yeah, the whole method is constructed about that for n data points, so there are some interesting criteria, like the last mode of crossing statistics is identical to chi-square statistics. The zero mode is the median statistics, and then the frequentist approach is a bit heavy computationally. It's difficult to use. It requires a hell amount of simulations. But yeah, I remember talking with one of my colleagues. I come up with the Daejeon interpretation, which is practically to say that, okay, I have a model, I have a test model, and I have a theoretical model. I multiply by a crossing function. If crossing function is consistent with 1, then I would say that my theory model is flexible enough. But if crossing function said, no, I need more modification on top of the flexibility of your theoretical model, then I would say, okay, now I can say that data suggests something beyond the flexibility of my model. Okay. So let's go to the DESI. you know, I developed crossing statistics years ago. It is original one is 2010, 11, and then I had two single author papers in 2012. When you are a young postdoc fellow, you can write single author papers. No hassle of arguing with anyone. But anyway, but I didn't use it extensively till the DESI data. So my team was heavily involved with the DESI. You've heard about the DESI. There was a pretty interesting results come out of it, in particular when it's combined with the cosmological background. We get this particular behavior that looks like that. We end up in this particular corner of WA. My postdoc, Rodrigo Calderon and Vishal Loda, who's my PhD students, they were very heavily involved. So we had two first author papers, one using reconstructing dark energy using the cross-sectional statistics. Another one was about the physics focus aspect of dark energy. So yeah, they were nice, interesting results. One of the interesting thing about the reconstruction that we use cross-sectional statistics on the dark energy density and the equations of dark energy, and we confirmed that the results from the CPA parameterization is valid. It's fine. Let's not forget, previously I said that yes, CPA can fail, but not for every form of dark energy. For the form of dark energy that apparently the data suggests, CPL works actually well. So either we are lucky or unlucky, I don't know, but for this particular behavior of dark energy, so both these papers were very much to test that, particularly the crossing. And some of the results from the crossing was very interesting. I think it's one of my favorite plots. That all the lines you see here, it has a fit to the combination of the DESI, union tree, and plot data better than the best fit lumpecinium. Okay, so I'm not saying that they are ruling out lumpecinium. I'm just saying that any line you see here has a fit to the data better than the best fit lumpecinium, better than the best fit lumpecinium. And there are models that the Q of Z is in fact crossing zero. The universe is not accelerating, it is decelerating. Of course, there was a phase of acceleration in the past, but the universe is not accelerating. And on diagnostic is something which we developed with Varun and Souradeep many years ago. When it is constant value, it's constant to the flat lumpecinium model. And when it's deviate from constant value, it clearly shows that you're deviating from flat lumpecinium. So yeah, this was a very interesting result. You know, personally, it was also interesting because this is a slide from one of my very old papers, 2009, again with Varun and Stravinsky, which was reported in Nature and Science at that time. At that time, using this constitution supernova data, we realized that okay, data suggests a strong particular behavior. And now after years, you see that yeah, I mean, it looks like very similar. So you know, maybe it's coming back that this cosmic acceleration is going down again. So yeah, this was a very interesting results. Then there was some physics interpretation. We explored some theoretical models to explain that. Among them, the Mirage model is very interesting. Mirage model is a model that you know, the fit to the CMB is very similar to the lumpecinium model, even though it has a very different expansion history at the low mention. And the model, you know, fit the data very, very. With the Bayesian evidence, it is very much a strong favor. So DESI 2025 DR2. Hubble tension persists. Just one slide on that. You know, when you assume the lumpecinium model, when you fit the data, DESI and the BBN, you can clearly see that you know things are still not coming up. Okay. Value. The contours for the CPL remain the same. Didn't change much. They were you know, people were talking that oh, you know, it's not about only DESI, it's about supernova, but they put this slide to mention that okay, only DESI and CMB also end up in this corner. And it doesn't. Zero. My team, Kushal and Rodrigo and William, they were leading actually this time an extended dark energy analysis. It was there's a supporting paper, which was very good. I mean, they worked really hard to do that, and I'm very proud of them to do the analysis because it was a very careful analysis. Even within the collaboration, we had to set the challenge that not every method could get to the paper unless pass the challenge. So Kushal generated the data, give it to people, said, okay, reconstruct that, see what you get. And there were methods who failed, and they were not end up in the paper. So we did lots of tests to make sure that the results are correct. There were, after DESI-DR1, there were lots of crap papers in the literature. Rush paper, I call them, that they wanted just to write something. And even it happened after DR2 as well, but less. Practically, yeah, what we see using the CPL, the same behavior as we see, we can see it in other parametric forms. I don't like these parametric forms, but practically they show the similar behavior. And when you use these non-parametric methods, like crossing statistics or Gaussian processes, you see the same trend, the same behavior. And this is the results, the bean W. So let's not forget, this is not about bean data right here. The W is bean. Okay. So one comment here is that the binning is interesting, but only along with the other methods. So it's hard to interpret results from binning independently or individually. Okay, so yeah, the results looks like that. We are in this corner, but something very interesting, which is very important from a theoretical perspective, and it's that if you are crossing the phantom divide line means W equal to -1. And why it is important? From a particle physics point of view, when you're dealing with the scalar fields, it's okay to have the equation of states equal to -1 greater than -1. But when you go to the phantom, the equation of states become lower than -1. We have problem with the kinetic energy, and that's difficult to explain. But if we do some tricks and come up with some phantom fields, but having something that it behaves in phantom in some domain and then go to the quintessence at some point, that is really, really difficult to explain. So then one question was that if crossing phantom divide line is real, because we could the data suggest this, and we tested the parametric method and non-parametric methods. So nothing wrong with the CPL. As I said, CPL is not always good, but for the particular behavior that we see in the current data, CPL is fine. But then we can have some quintessence models which can generate such a behavior. So these models work much better than the lambda CDM model, but they are not as good as the CPL. So we try to address this question. I said that how to compare models that are not nested within one another. So imagine that you have the CPL and I have this model pod W. They feed the data in a different way. One is better than the other one, and then how can we deal with that? So what we try to do, we try to simulate 1,000 realization of data based on the quintessence. So we made 1,000 realization of data based on this pod W. And then try to feed the data by both CPL and pod. Okay, and the result was interesting. Even though that the data was based on the pod W, in 36% of the cases, CPL feed the data better than the true model. Okay, so the point is that pod W allow deviation from the W-1 at the lower redshift and doesn't have much flexibility at the higher redshift. And while the data has large error bars at the higher redshift, as a result, you may end up by having fluctuations around the higher redshift that the CPL can catch and pod W cannot catch. So yeah, that would be very interesting result to understand that, okay, 36% of the cases, CPL with phantom crossing has a better fit than the true model. And in fact, in about 3% of the cases, CPL yields a delta chi-square, even larger than what is observed. So the true model could be pod W, and the CPL can indeed fit the data better. And the probability is not that small. 3% is not that small. So yeah, so this is a very important point. So these are the cases, right? And these are the cases that the CPL fits better than the pod W. The red one is in fact where the true model exists, actual data exists. So this could be the case. So let's not forget, we are not saying that the crossing the phantom divide line is fake or wrong. It is highly probable, but still, it is not very decisive. Still, there is a chance, there's a good chance that underlying model can be not crossing the phantom divide line. but because of the sparseness of the data and the statistical fluctuations, we might prefer CPL with the phantom crossing to the original model, which may not cross the phantom. Okay, my conclusion. There are now tantalizing hints for dark energy evolution. We spent good time to find the word tantalizing because we don't want to oversell things, but we want to coin the discovery. If it is really dark energy evolution, DESI is the one who found it. Data suggests crossing of the phantom divide line. It's an uncomfortable situation theoretically. There are other viable solutions are not yet ruled out, and the actual significance of phantom crossing is not yet very high. So as I said, there's still about 3-4% chance that the underlying model might not be the model crossing. Will these remain significant? Well, DESI year 3 DR2 confirmed the initial finding, which I think is very important. After loads of crap papers which come up after the DR1. I was one of the people who said I don't care. I was not really paying much attention. Because after a while you reply to one paper or two paper, but then you realize, okay, they are coming every day. People are looking for citations, so let them be. The truth will reveal itself at some point. So Hubble tension remains a separate but connected issue. So to me, Hubble tension is there. I'm caring about that. There are issues in cosmology which are interesting, like a statistical isotropy of the universe. Hubble tension is there, but yeah, I mean, we try to address things, not to mix the problems, right? I mean, again, one example I give to my students is that if there are multiple problems on top of each other, you may really end up with the wrong medication. Which can be the case, right? Imagine that you have a patient which has two different sickness at the same time, and then if you want to interpret the symptoms, it would be very difficult. You don't know the headache, for example, is coming from that viral infection or that bacterial infection, which are sitting on top of each other, or if the stomach upset is coming from which one, right? And then if you have symptoms for multiple problems, then breaking the news is very. So yeah, Hubble tension has remained separate but connected issue. So new props, model-independent consistency between various data is essential to rule out systematic. So for the Hubble tension, I would bet personally on systematics. I don't know which data, but yeah, it might not be just true. But about evolving dark energy, I hope it's true. It will be very interesting and exciting because not only it would be excitement for cosmology, but also it allow us to continue working on cosmology. Imagine that everything is fine with Lambda-Cidium. No one give money to cosmologists to work. There's nothing much to do. So yeah, it would be nice to have some excitement. So yeah, so that's how. Thank you.
Oh, thanks, Arman. It was a very interesting talk. I got to learn a little more of your statistical techniques that you employ. One question, I mean, yeah, are there any questions from the audience? If anyone has any questions, please. Okay, I have one question. Yeah, someone is about to ask something.
Hi, Arman. Nice talk.
Hi, Joby. Good to hear you.
Hi.
See you. I cannot see you.
Can you hear me?
Yes, I can.
Okay.
Yes, I can.
So I was curious about the crossing statistic. I didn't. While I think I understand what you mean by the order. Like chi-square doesn't care about the order or the sequencing, right? But I didn't understand how you convert the sequencing into a number, into a statistic. Do you mind?
Well, sure. I can tell some very basics of that, Joby, but don't expect me to explain like 5 big papers.
Like just some idea.
Yeah, exactly. So the idea is that do I have a slide? Check it. Cool. Okay, cool. Yeah, I have something. So first we go to the residual space. Okay. And then we try to divide the data. So first of all, crossing statistics would have n different order, right? Let's focus on the order, not 0, order 1. Okay. Order 1 means that there is one crossing. I assume that there is one crossing. Okay. So if there is one crossing, I try to find n1 that my Tn1 is maximized. What does it mean? Is that, let's go back to the data I showed. So first of all, I care about the normalized residual. Normalized residual means that I subtract the model by the data divided by the right. For example, here all the normalized residuals would be 1, 1, 1, 1, 1, minus 1, minus 1, minus 1, minus 1, right? So then I said that I put a crossing here. If I put a crossing here and I summarize over the residuals, this side, the left side, will give me 1, and the square of 1 become 1. And the right side give me 1, 2, 3, 4, and then minus 5, minus 1. So if I put a crossing here, my T1 would be 1 square plus 1 square, which become 2, right? If I put the crossing here, I would have 2 here, and I have minus 2 here, right? So now 2 plus 2 square and minus 2 square become 4 plus 4 become 8. In fact, if I come to the middle point, I would have plus 5 here and minus 5 here. So this one become 25, this one become 25. So my T1 become 50. So maximum T1, which I can get from my left plan figure, is 50. But what about the left one, the right one? The right one, if I put it here, here is 1, here is minus 1, so it's 2. Here, this part is 0, they cancel each other, and this part is 0. Again, if I come here, this part is again 1, this part is 1, 2. So you see that wherever I put my crossing point, I cannot exceed 4. Okay? So T1 statistics, in crossing statistics, basically says that find out the point that your T1 statistics become maximized. And what is T1 statistics? Means that I divide my data and I go to the residual space, summation of my residuals, square of them. So let me show the equation again. Here. So these are individual data, and I'm maximizing on my T1. So this Q1 and Q2 are one side of the data, left side, right side. And I maximize them, square. So in that example, the T1 of the left plot is 50, maximum T. And if I basically do 10,000 realization of the data, it would be very rare to get 50. And of course, it was just 10 data points, not that rare. But imagine that there is more of them. But if you go to the other side, you get just about 4 or 5, which is very interesting. And this can be used to test the hypothesis.
I see.
I mean, if you need, yeah, I think this paper is about, yeah, the core of it.
Okay. Thank you, Arman.
You're welcome.
I have a question, Arman, regarding individual preferences of these data sets. For example, there is also now the third one that is emerging, CMB, and then you have the supernova, and then the TRG data also is now being plotted along with all those. So it is emerging as more reliable probe of cosmology. So it has a preference about 70. So it is sitting midway between these. So what do you think about these individual about the preferences of these individual data sets? I mean, when you combine them, perhaps they just, even though they are pushing and pulling in different directions, they may just give something that is consistent with that. I mean, mixing many things will give you something. So do you have any comment on that?
Yeah, I think it's a very good point, Pawan. I mean, my personal attitude is that let's be humble towards science. So, what I mean is that, data suggests something, and we may come up with some theory, or we may come up with some ideas, right? But I think it's very important not to stick on that, not to get emotional about it, right? So TRGB certainly is a very important probe. Even understanding its uncertainties are very important. We have a volume issue. So it means that the volume which we have to observe to reduce the uncertainties is an issue. That's why it's a very slow moving field. As you said, you know, their current constraints are basically around 70, so they're fine with everyone, right? So they found the middle ground. But yeah, certainly new probes, they can be from gravitational waves. If we find, you know, some neutron star binaries, right, with the electromagnetic counterparts, if 10 of them we can have a new probe of H0. If we use a strong lensing, so yeah, there are new probes coming. They can have different systematics, and what we found now, it may remain or it may washed away. So we should not just stick to that. I mean, we should try to understand the systematics as much as possible and report what we find. And theoretically, we should not really get emotional or attached to models. As you know, they may come and they may go. I mean, I remember that, for example, this one. Okay, so for example, the middle one is my JEDA model, generalized emergent dark energy. It's one of my favorite dark energy models which I introduced, and it didn't work. It didn't work, right? I mean, you know, I remember that Kushal was saying that, oh, Arman, your model doesn't work. Okay, it doesn't work. I mean, what should I do? I mean, I cannot get depression about that, right? And I even included in the paper, it doesn't work. It may come back at some point. It may come back at some point. I mean, as I showed about this slowing down, right? This is slowing down when we proposed that, you know, after a while it was washed away in the sense that they changed the covariance match of the data. But now we see that after 15 years, you know, we may see the same effect, right? So we should be just humble to the science. You know, we may find something and we should be very open-minded. I mean, you know, which I think is a healthiest approach. So that's why even about the DESI, some people said, what if DESI has systematics? Okay, we try to find out, right? If there are some systematics or there are some issues which we have not yet noticed, it would be great to notice them and correct it. But so far, and let's not forget that, for example, with the DESI, the analysis was done in a purely blind analysis. Means that, you know, the pipelines were tested and they were basically fixed. When the data passed through the pipeline and the result was released. So it's not, there is no massaging or adjustment after understanding it. And I think it's very important. It is very important, the blind analysis.
Yeah. So, have any other questions? Okay, if there are no further questions, so let's thank the speaker. Arman, thank you for taking
very
time
much for
to
inviting me, and thanks
stop.
for hosting, Pavan,
Yeah.
and thanks to see you, Joby, everyone. I don't know if I know other people here, but anyway, nice to see you all. Send my hi to Tarun and others. You know, happy Durga Puja, and
Yeah.
and I will respond to your email. Oh, hi, Joby, good to see you.
Hi, nice to see you too.
Okay, thanks everyone.
Yeah, see you then.
Thank you. Bye-bye.
Thank you.
Bye.
Thank you. Goodbye.